Today, some evidences that reinforce the possibility of a role of Pisa and Venice in the development and diffusion of Portolan maps. The presentation is based on a tool that has been found in Italy, in Verona, in last century, 100 years ago, but is related to the 13th century. The representation of their surface, latitude and longitude, and the use of this tool for the representation of geographical data and gathering of geographical data. Then I will discuss a possible role of Fibonacci in the development of these techniques and why Pisa could be a good place for generating this kind of maps. The story starts with a tragedy. An airstrike on Verona in 1915 revealed a secret room where there was a cache of weapons and armors. And together with this equipment for an army, there was also a strange tool. It was considered as a hanging lantern, for a device to hang some lamps on it. But I will show that it is a mathematical tool that can provide the Qibla. The Qibla is the direction towards which the Muslim has to point their carpet to make their prayers. And there is an engraving on the tool. That is this mark that shows that it is a Qibla. It is the symbol of Qibla on the right. And it contains the rules of projection that were devised for the first time by al-Biruni, a major Islamic scientist of the Islamic Golden Age. The presence of these tools in the 13th, 14th century in Verona, a town that is faithful to Emperor Frederick II, like was Pisa, and the presence of this Islamic piece witnesses the change of information between the Latin and Islamic civilization. So this is the same period in which Portolan maps appeared in the practice of navigation into the Mediterranean Sea, developing new perspective to the commerce. And so we'll see how these two findings, the tools in Italy and the Portolan maps, testify that this is change of knowledge. This contains several references to the possibility to the measuring of bangles. It was possible to open the instrument, and on the right you see a system that could hold a lamina of silver, possibly with engraved marks, and these rings on the sides that can hold a map. Another detail of the construction, this point on the top of the instrument, is similar to the mirah, that is the shape of the niche into the mosque that indicated the direction of Mecca. How it works? What we have to observe that the external sides of this tool represent two meridians, the -30 and the +30 meridians. That the equator is represented by the horizontal bar, and the vertical bar represents the zero meridian. The author of this instrument was well aware of the deformation that derived from an orthogonal projection, and probably set the inner part of the instrument to delimitate the area where the projection were at the less deformation. But how it works? If you make simply an orthogonal projection of a set of points on the Earth's surface, like I made for the Mediterranean Sea, where I have obtained 10,000 points on the coast of the Mediterranean Sea that have been the base of my comparison, you see that you can get a map of what you want to represent. But it is an XY map. Cartesio, Descartes was not born yet, but al-Biruni had devised a system for utilizing this data. He had also found a value, very similar to the value that we adopt nowadays for the ray of the Earth. And he was a master in the application of the Ptolemy's theorem to the construction that can be made on a sphere. The Ptolemy's theorem states that if a trapezoid, a quadrilateral, can be inscribed in a circle, the sum of the products of the sides is equal to the products of the diagonals. And this can be used both for making representation of geographical data, but to get unknown values of longitude. What lacks to these instruments? A map of the meridians. I made a map on the chart in this case that represent the fine graduation that could be available on a lamina of silver inside this instrument. The system probably also lack a nullidate for the evaluation of the angles. That is the lamina in another instrument that I have substituted with a chart. And we made easy measurements by using magnets and threads. How it works? With reference to the graduation reported on the sides, on the ogivas, you see the different latitudes in white figures. You have, first of all, mark the latitude of the 2 points for which you want to find the Qibla, let's say, of B respect to AE. Then you have traced the corresponding lines. Then you have to compute half the difference of longitude, so you refer everything to the middle, to the zero meridian, reducing the deformation. Then you can place on the net the 4 points A, B, and C with these coordinates. What you are interested to do is measure the distance of A from B. That is the distance on the local sphere, the sides of the sphere on which the instrument represents a projection, is 21 centimeters. We see that this value is a K roll, and the distance can be then referred to the distance on Earth. Distance A from B is the distance, the so-called orthodromic distance, so the distance on the plane of the 4 points. What we need is the distance on the arc, but it is a matter of spherical trigonometry to refer the orthodromic distance to the losodromic distance, reporting everything to the ray of the Earth. When the Qibla finder is suitably oriented, it can be oriented with the method of the Indian circle, for example, during one day. The direction that is pointed by the segment connecting A and B indicates the Qibla, while the distance is provided by the measurements that I have talked before. If you want to do exact computation, you have to rely on the tables and solve this expression for obtaining the value of the arcs and of the angles. That is the value of the Qibla. These are some comparisons that I have made with this projection for estimating distances, and this distance that can be obtained on with Google Maps, for instance, or applying the equation of Vincentis to the ellipsoid, UGS 74 ellipsoid that represents the Earth, and it is commonly adopted for the projection that we use for the whole Earth. As you can see, when you provide latitude and longitude, you can see that the error is very small, and there is a larger error only for the points more distant. See, for instance, the difference for Venus from Mecca, or the distance from Sana from Mecca, that is a lower distance, and the concordation of the 2 meters is very good. Also, the azimuth are very well evaluated. So, the tool, why it was with the equipment of an army in the secret room? Because it had a strategic value. It could be used for determining the distances and the time of performance of locality during the attack of an army. But it provided that you have available the coordination, the coordinates of the points that you want to connect. But I asked at this point, why not to use it for mapping? If I already have the coordinates of a point, it shows a reference point for my representation, I can obtain azimuth and distances for every point that I want to represent. This is what I have done with my data on the Mediterranean Sea. This is the result of plotting latitude and longitude after transforming them in azimuth and lorthodronic distances. These are maps that are very different from the Ptolemaic maps that have a more pronounced difference of longitude from for Italy, or for the whole size of the Mediterranean Sea. And this is the difference between orthogonal projection and azimuthal equidistant projection. That is the kind of projection that I have obtained with this method. A projection that was proposed for the first time by al-Biruni, who proposed also the distance. So I asked him, why not to try to see what is the age of this kind of projection? If there is a map that can be superimposed with my projection, that is the age of the projection, or that is the projection of the map. And this was the first time I was in contact with Portolan maps. I take here the Carta Pisana, and I checked before if the angles were preserved with this context. Then I devised a system to make comparison. I used the Portolan map, or the base map, as a background for the whole diagram. So I have some key points on the background of the diagram. I identify the same points on my maps. Then I provide a rototranslation matrix that has to provide the fit of 5 selected points. You see with the same color on the Portolan map is the tip of Corsica, and on the projection of geographical data. And so the other point along the map have the same meaning. Similar localities on the 2 maps. If by minimizing the sum of the square of the distances between corresponding points I can obtain the convergence of the map, that is the way of projecting the map. You see here what happens. Okay. There is some discrepancy in the northern coast of the Black Sea. You see, but the correspondences, and some also difference on the France coast. But the correspondence, I was struck by this correspondence. It is not only provided for the map, for the that I showed before, but for a series of Portolan maps that I found on the net. You see here? This, where I adopted a point of projection very far from the position of the Portolan map, also provided a very good representation. And this is amazing, for instance. This is because the center of projection is in the center of the map. So what I guess is that these stars or points are the lines along which the distances are preserved in azimuthal equidistant projection. This means that probably different areas on Portolan map that do not correspond